My name is Kristen Erickson, and I'm a member of one of the organizing committees of this symposium. It is my extreme privilege to introduce today's keynote luncheon speaker. Now, the scientific community knows Dr. James Green in several ways. As a renowned solar physicist with over 150 peer-reviewed papers, as the director of NASA's planetary science, and as such, the chief Washington spearcatcher. We also know him as the visionary leader that successfully launched over $4 billion of scientific missions last year alone, one resulting in the successful Mars Curiosity landing in August, and another, Juno, that, thanks to Jim's foresight, will be in orbit around Jupiter when Cassini is in a comparative orbit at Saturn. What may not be known is that Jim is also quite the history buff. He is a recognized expert in Civil War balloons, and with this 150th anniversary year of the Civil War, he is in quite demand as a speaker in that arena. So with this intersection of his interests in science and history, we are in for a real treat. Now, to hear his unique perspectives is Dr. Jim Green.
Well, it's just wonderful to be here on the 50th anniversary of planetary science. And I thank Kristen and also Stephen for helping pulling together some of the statistics and mission information that I'll be showing today. I think it's well known, but it's well worth stating that NASA literally invented planetary science starting in 1962. Everything we knew about planetary science up until then, we got from the back of a telescope, and even Percival Lowell got it wrong. Our ability to launch missions has provided us the opportunity to get up close and personal with many bodies in the solar system. And of course, there are many more that we're discovering, and there are many that we'd like to interrogate much more thoroughly because of the importance those bodies are in our understanding of the origin and evolution of the solar system. Well, we've heard about today a little bit about the decadals. And here are three important NRC documents that I would consider are the planetary decadals, the last three planetary decadals, the only planetary decadals. And in fact, the very first one was done by Joe Burns and a collection of scientists talking about the important questions of our field and some of the approaches that might be taken, but it doesn't talk about the missions that are needed. You know, in that integrated strategy, there are the top things that we need to know, but there's no costing of missions. There's not, this is the next one and has to go to Mars and it needs to land on the surface, etc. And from that perspective, that particular document did not enable, I believe, the planetary community to move significantly forward within the political environment. As we entered the early 2000s, the next decadal, chaired by Mike Belton, New Frontiers in Solar System Exploration, really began to provide the framework that was necessary to move planetary science forward on many fronts. Not only scientifically, because all the scientific top questions were in it, just as the previous study report, but also what we would call conceptual missions, how they were going to be done. Now, that particular report, which went from 2003 to 2012, was very valuable and enabled planetary science to be put on the map in many different ways and move significantly forward. You could walk into congressional staffer's office and see it on the shelf. And they would pull it out and they would say, "What mission are you talking about?" So that framework, the ability that the NRC has to be able to create a strategy, the overarching plan for planetary science that delineates missions of importance, that does answer the important scientific questions, was a real winner for the community. Now, the last report, the one that's been recently issued, Visions and Voyages, that was chaired by Steve Squires, and it had an enormous number of people in the community participate in it. We concentrated significantly in those missions and the mission architectures. We costed those out at a much higher fidelity than we'd ever done before to try to understand from a cost perspective how to be able to create a program that is responsive to the science questions and yet affordable in the times that we felt the funding projections from the president were given to us in 2010 when the report was really completed and the analysis of missions moving forward. The report also has a number of important aspects to it in the sense that it has, what do you do when the budget isn't as rosy? So there are decision-making rules. So there's going to be a lot of discussion as all the decadal reports are discussed and how we're going to move forward in the next major sets of decadals and whether these approaches will work for us and whether decision-making rules need to be much more clearly delineated for us to be able to use within the next 10 years. But it's extremely important to note a couple things about this. One, the planetary community is behind Visions and Voyages, as they were behind New Frontiers in the Solar System Exploration Report. That allows then, out of those four elements, the science, the administration, the administrator of NASA, and Congress, it allows one of those legs of that stool to be solid. We know what the plan is to move forward. And that's the science community. And that is really quite critical and is the foundation of everything that moves forward. Now what's happened is this particular decadal, Visions and Voyages, actually starts in October. All right? It's got 10 years. And even though our budget projection wasn't as planned when the report was near its finishing date, we have 10 years to live this report, and we have 10 years for the community to get behind it because the science is incredibly exciting and incredibly compelling, and our community is united as we move forward. So that's an important aspect, I think, to really delineate. Now, what's happened in those 50 years is an incredible revolution. Absolutely unbelievable, as I've mentioned. We've had the opportunity to go places and to see things and to do the analysis. And in fact, what you may not recognize may sound like a jumbled set of missions. Well, are you going to land here, or are you flying by it, or are you orbiting? What are you doing? But in reality, there's been a methodical approach. And that methodical approach is flyby, orbit, land, rove, and sample return. And that particular approach, even though we don't talk about it much in the science community, is really quite obvious when you stack up the missions and you see what we've done and we know what the next major steps are. Each of these, flyby to orbit, orbit to land, land to rove, are huge steps. They are major steps in science also, in our ability to do the next element, the next answer, the next most important questions from the preceding set of missions. And I hope to be able to illustrate that in many different ways. Now, planetary science, our goal, is stated here, is advance our scientific knowledge of the origins and history of the solar system, the potential for life elsewhere, and the hazards and resources present as humans explore space. And that's a theme that you'll see throughout this Visions and Voyages decadal as we move forward. Now, over the last couple years, and in fact we call this the year of the solar system, it's a Mars year, so it's about 670 days. That's right, it's a planetary approach to things. We've really accomplished an enormous number of missions and mission objectives. And from these missions, the data is starting to come into the archive, and the scientists are beginning to reap those benefits. Now, just as an illustration, let me point out a couple of these things. We've flown by 2 comets, and we've learned an enormous amount, surprises in each. We've launched 3 missions, Juno to Jupiter, Grail to the Moon, and MSL to Mars. We've also inserted in orbit Grail to the Moon, both Grail A and B, named by kids, Ebb and Flow. We've inserted Messenger into orbit around Mercury. And we've inserted Dawn around Vesta, the second largest asteroid. In addition to that, we've pulled Dawn out of orbit from Vesta and moved on to the next and largest object in the asteroid belt, Ceres. Another really exciting body that will tell us a lot about the origin and evolution of the solar system. And we've landed MSL, Curiosity rover, safely on Mars. This is just an enormous set of achievements, absolutely enormous. So we have quite a bit of success. I think it's a testimony to the hard work that's gone on in all the centers that participate in these and throughout the scientific community to make these missions and activities so vital and so successful. And as I mentioned, the science data will be flowing into the archive on a continual basis, and new and greater discoveries are going to continue from those. Now, I'm going to show a number of charts like this. On the horizontal axis, we have the object, in the inner solar system, Mercury, Venus, our moon, Mars, Phobos and Deimos. And on the vertical axis is the approach, flyby, orbit, land, rove, and sample return. And what's listed here, this is not meant to be an eye chart, but it shows you, I think, the missions from an international and NASA perspective that have been launched to effectively interrogate our solar system in this way. Now, what's also shown in blue and highlighted are those elements, are those missions from the Visions and Voyages decadal, which are the big steps. For Venus, it's a Venus in situ explorer. For our moon, it's getting back down to the surface through sample return in the South Pole Aitken Basin or a geophysical network. For Mars, as you can see, it's sample return. We are there now. We now know enough about Mars to know where to go, the kinds of things that we need to take with us to analyze what we find and make decisions on what samples we need to bring back for further analysis. And we've recently selected InSight, which is a one-node geophysical network, also well described in the planetary decadal as a discovery mission. Now for the moon, as I mentioned, both the geophysical network and South Pole Aitken Basin are prominent in the planetary decadal, and of course for good reason. These are big steps. These are indeed the next things we need to know about the moon. And of course the moon has on it really the history of our inner bombardment of our solar system, what's hit the moon, its size, and its shape, of course, has probably also hit the Earth. From the lunar rocks that we've brought back, from the samples that have been brought back from the Apollos, more than 800 pounds of rocks, we are continuing to do that analysis. And we are finding now much more information about the origin and evolution of the moon. And we're also realizing that in addition to the initial creation of the Earth-Moon, which we believe occurred from a collision of a Mars-sized body with the Earth and the reaccretion then of two bodies, we call the Earth and the Moon, at about 4.5 billion years ago. We also recognize that about 500 million years later, a major bombardment occurred in the inner part of the solar system with asteroids, comets, and perhaps even Kuiper belt objects, bringing a significant amount of water with it. At a time when the Earth had cooled and was ready, based on its gravitational structure, to be able to maintain and hold this water, and creating the water planet that we know. So perhaps anywhere from 40 to 60% of the water that's in our oceans has come to us through this type of bombardment. And these are the things that we are learning, and these are the understanding that we are obtaining through the analysis of samples and through the analysis of other elements and other missions that are giving us this important perspective. We're, through the Lunar Reconnaissance Orbiter, making detailed observations of the moon. They could easily see these two tables from orbit. And these detailed observations are incredibly important when we combine them in other ways. This is an altitude map of the moon that allow us to, again, effectively do the next two New Frontiers missions, and that would be South Pole Aitken Basin sample return and a geophysical network lander. In fact, what you see on the near side of the moon as compared to the far side is a very different structure. The mare on the near side of the moon are basaltic, volcanic, if you will. On the far side of the moon, much different structure. In fact, the blue area, which indicates the lower latitude on the backside of the moon, is called the South Pole Aitken Basin. It's a huge impact region. And between the depth of that basin and the white area, which is the highest altitude, also on the backside of the moon, is more than 19 kilometers. And that's a distance that's larger than the top of Mount Everest and the bottom of the Marianas Trench. So it's a huge distance. And in fact, in the South Pole Aitken Basin, we believe is the lower crust, perhaps material from the lower mantle, and it'll tell us a lot about how this body was put together, and that's an important element of planetary structure. We can't even get to the mantle of our Earth, and yet elements of understanding how that body was put together is laying on the backside of the moon. We also, with the Grail mission, have taken a good look at the gravity of the moon. Our two spacecraft, as they pass over and are affected by gravity and change the distance between them, enable the scientists to back out the gravitational structure of the moon, not only in its crust, as shown here. In fact, the best estimate we had of the lunar gravity came from Lunar Prospector. It's shown on the top panel. Grail, after 1 month's worth of data, and right now it's on its 6th and 7th month of observations, gives us the kind of detail and resolution that we need, that when we combine the LRO data, allows us to do precision landing, allows us to put something down on the ground, on the moon, within the distance of this room. So really tremendous results now from our missions are coming into the archive that indeed enable us to build more exciting missions into the future that are of decadal importance. As we look back at Mars missions, we see we've flown by, we've orbited, we've landed, and we've had rovers. And indeed, the next big step is sample return. Our knowledge of Mars has increased significantly. We have a whole session about Mars. And of course, our perception of Mars has changed. From telescopes, Percival Lowell thought that there perhaps was a a civilization in crisis based on the fact that he interpreted features that looked to him like canals, transport of water throughout various regions on Mars. That turns out not to be the case. We were perhaps even more disappointed in the earlier flybys, which made the moon look much more made Mars look much more like the moon than what we know about it today. Well, we've put together a program that follows the water, looking for signs of water on Mars, and we recognize that those structures are everywhere on Mars if we only had the resolution, which we do now, to see. So there are many observations now that we've been making over the last 10 years, well rooted in our last planetary decadal, that's providing us now the information we need to be able to go back to Mars, go to the right places, and bring back samples. And in fact, what's even more exciting, even though liquid water as we know it should not be able to exist on the surface of Mars because the pressure is not such that it can stay a liquid, it evaporates quite quickly. And in this particular example, as you see, a number of observations, seasonal observations, over about a year of a particular region on Mars, and there are many like this now, in a sloping area, a crater on Mars. We see these lineations, we call them that, but in reality we now believe that these are, in the summer, where water, briny water, can exist at this pressure, flowing down, indeed, the sides of these craters. So, where has the water gone on Mars? It's gone underground. And as we now know more about how the water cycle and the hydrological cycle on Mars could have existed, it also has evaporated and been stripped by the solar wind because Mars's magnetic field had left the planet many billions of years ago. So in understanding a number of these physical processes at these planets, we also now understand a lot more about our Earth and the importance of our own magnetic field and the importance of how climate changes on our Earth. Also, over the last 10 years, even our ground-based telescopes have made productive observations. What you see on the left panel is Mars, but it is color-coded, red being the highest intensity, blue being the lowest intensity, of a trace gas called methane. And these methane observations have been observed. They're very controversial because they are from Earth, and we have to look through methane to see methane on Mars, so it's very difficult to separate. But they've been done very methodically and I believe very carefully over the last 10 years. And they show that Mars goes through methane emission cycles, and that cycle is periodic, with the most intense methane emissions occurring during the summer. So those variations are seasonal. The explanation of methane, of course, there are a couple. One, it could be biological. Are these microbes that are indeed generating methane? Or it could be abiotic. It could be regions of minerals and magma with water, underground water, and we certainly see from these leaking of the aquifers the major amount of water locked in Mars's crust. Perhaps that's generating the methane, and that certainly could be the case too. I believe we're on the edge of understanding the methane emission because Curiosity rover, which is also now on the surface of Mars, has the ability to make these trace gas measurements and, more importantly, also observe their isotopes. And there's a biological sorting that goes on in these isotopes. And that gives us an indication, more so than ever before, of the reality of where the methane is being generated and how that might be related to either geological activity or biological activity. So we'll see, I think, major steps in that direction as Curiosity continues throughout the spring and summer and winter season of observations. So truly, truly exciting, and once again, tugging on our interest of, is there life beyond Earth? Curiosity's landing, of course, was absolutely spectacular. The response from this nation and many, many other nations was really quite gratifying. There are countries in this world that dream about the stuff that NASA does. NASA has such a branding, if you will, when you go to other nations and talk to people in the street and the public. The admiration is unbelievable. There's no politics in it. It's all purely science, fascination, inspiration, and interest. And it's because we do some of these things that are absolutely astounding because we need to make progress in the science questions that we want to answer. So engineering feats enable our science in many, many ways. And curiosity is a perfect example of that. The engineering feat provides us an entree into the public to discuss the science that we are doing and share in the excitement with what we are finding out about each and every one of these bodies and how they relate, of course, to our life on this planet. As we look into the outer solar system, we see Jupiter, Saturn, a number of their important moons, and small bodies and comets and asteroids. And once again, we've discovered many, many things, primarily from flybys. But in the decadal, the vision and voyages, there are a number of important missions in terms of now the next step, orbiters. We want to be able to orbit some of these objects like Europa. We want to be able to orbit Enceladus. We want to be able to set down various things on Titan and also interrogate its atmosphere. And in fact, if we take Titan as an example, we had an opportunity to break the paradigm of fly-by, orbit, land, rove in a methodical fashion with Cassini and Huygens. With Cassini, as we flew by Titan, we dropped off the Huygens probe, which actually got down to the ground and landed and made measurements on the surface, not knowing exactly where it would end up, not knowing if it would end up on a hill or in a methane lake. We believed there was lakes of methane there, and of course there are, but not at that location. And we did not know if Huygens was going to survive. It had primarily atmospheric measurements to make so that we could actually get a good idea from a remote sensing aspect. But indeed, it landed and survived for a period of time. That was really quite exciting and very important and enabled us now to think of new things that we could do at Titan and that we want to do. And we see that in some of our proposals that come into our discovery calls. And once again, those elements that are in blue are those things that are in the Visions and Voyages document, our next big steps. And the JUICE mission, that's an ESA mission, is also shown there. It's going to end up orbiting Ganymede. Ganymede is our largest moon in our solar system, generates its own magnetic field. It's an ice world. It's much more like, we'd say, Callisto and Europa than Io for sure. And so it is a fascinating object. Flybys by JUICE of Europa are also planned and should be quite exciting. And I'm delighted to say NASA is a part of that of the JUICE mission, which is the Jupiter Icy Moon Explorer mission. In the area of comets, the decadal delineates sample return as important elements. And we have done sample return already with the Stardust mission. One of those things that we were able to leapfrog in this paradigm and be able to do by flying through the coma and bringing back material that had been analyzed. And now we see another fabulous opportunity, a huge comet called ISON. Its perihelion is next year in and around Thanksgiving. And the prediction, based on the fact of how bright it is right now at 6 astronomical units away, it's even further than the planet Jupiter. It's already at 18th magnitude. And how close it gets to the sun, which is only 14 million kilometers, very close to the sun, that this comet will have a huge tail, many tens of degrees, and may actually be observable during the day. That will capture attention across the world, and we're marshaling resources to take a look now of existing assets that we might be able to make great measurements, and that includes investigating some potential balloon observations, also near and dear to my heart, as Kristen mentioned, where we'll go up and hopefully have instruments available to take a look at these at ISON, along with other objects in the solar system, in new and unique ways, in a quick reaction capability, much quicker cadence than building a mission that takes many, many years to do. Here's our collection of comets that the international community, NASA and ESA, and Russia have, and also JAXA, have observed. And you can see their structure is quite different. These are typically small bodies, 10 or so kilometers or less in their largest dimension. And we've flown by most recently, going back to Temple 1 after we had an impactor to see the results of that impact. We've done that, and that data is being analyzed. The new comet that we observed over this last year was Hartley 2, and Hartley 2 was tremendously exciting. We've also, from Stardust now, examined material in detail because we have those samples in our lab, and now it's clear that amino acids, and particularly glycine, has been discovered from those materials returned from WIL 2 from the Stardust mission. So these are incredibly exciting missions, and they're really telling us a lot about how potential water came to this planet and the potential building blocks of life, more complex biomolecules coming from comets and other elements of the solar system, asteroids, and as they have bombarded the Earth over time. And that has occurred throughout our solar system. So it gives us the impression that the conditions of life may be ubiquitous given the opportunity and an environment, an envelope of an environment to survive. And over the last 15 years or so, we've invested in the astrobiology elements, bringing people from planetary science and biology together to really tackle some of these tough ideas of how life could have been created and look for life here on Earth in the extremes. And we're making major progress in that area. I want to go back to Hartley 2. This is our most recent comet observations. When the comet scientists saw this particular image, they were absolutely dumbfounded. Comets, which have a lot of volatiles, water in particular, and ammonia and other elements that once they heat can sublimate quickly, in other words, go from solid into vapor, do so on the sunlit side of the comet. And when we look at this particular comet, we see jets of gas coming from the dark side of this comet, coming from regions that are not in the sunlight, but must somehow be warmed within that comet that then breaks out and pushes material outward. And in fact, here's a high-resolution blow-up. There's several frames here that show you what's happening coming at a little distance away from the particular comet. And when we analyze this, this is not a star field background. The speckles that are in this image are cometary material, things the size of golf balls to perhaps as big as volleyballs. We're watching the end state of a comet completely dissipate within the solar system. It is flying apart. This comet has a period of about 6 years, and many of the comet scientists say it will probably not last more than 100. But all its material will be scattered through the solar system, and in some cases we actually orbit through older paths of comets, and material also comes to the Earth, and we still see the excitement of being able to go out in the field and bring back some pristine material, even though it's passed through our atmosphere. In the near-Earth objects, we're learning a lot more about how these are fundamental pieces of our solar system. Here is observations of an asteroid called Itokawa. And when you look at that, this is not a cratered-filled body. This is a body that has accreted material and has produced an enormous amount of excitement about these loosely packed, gravitationally centers of material that come together that form these objects as part of a building block to even larger ones. And of course, we're quite interested now in building that next New Frontiers mission, OSIRIS-REx. That's on the books, and it's moving quite nicely forward to bring back samples from also an important comet, a C-type asteroid. Here are the asteroids that our spacefaring nations, NASA, ESA, JAXA, and Russia have observed and visited, some on the way to the outer planets, some intentionally targeted. And what's circled off to the side is the comet Hartley 2. So you can see the size of these are very different. But as we see comets now, we may see larger ones from out in the Kuiper Belt eventually come towards us. We're quite excited to understand how large Comet Ison is, and it may be one of the largest comets that we've ever seen, and consequently, one of the more exciting objects and something of a lifetime to observe. Now, I did want to point out one thing. The largest body on this in this set is the asteroid Lutetia. It was observed by Rosetta, and in this particular comparison, Lutetia is the one on the far left. It's very small compared to Vesta and Ceres, which are also asteroids, and then, of course, in size, Pluto and the Moon. So it gives you a feel for the size range of objects that are important in the solar system, and they come in all sizes. But Vesta is incredibly important. Dawn just left this object, this second largest asteroid, and on its way now to Ceres, the largest object in the asteroid belt, which is about twice the diameter of Vesta. From the mineralogy, and as they look at the surface, they can tell some of the bombardments have also brought perhaps hydrated materials onto the surface. We now know from orbiting Vesta for nearly a year much more about its internal structure. We believe it has an iron core. That iron core may be more than 2/3 the size, or perhaps a half, to a little larger in size inside the body. So that means this particular body is differentiated. The higher mass materials moved into the center of the body, and we would now look at this object a little differently as more as a building block of a planet, as a planetesimal, one of the first things needed before a planet can be accreted and complete. And in fact, as we look at the asteroid belt is not necessarily made up of material that just is blasted apart, moons that or objects that or planets that were there in the past, but in reality, it's a set of material that is trying to become a planet, but Jupiter is not letting it happen. Jupiter's gravity is keeping it apart. But so when we go to the asteroid belt, we're actually going back in time and seeing some of the early processes. The Earth must have started out in this particular way and evolved. So let me end in the time I have and now show the total view of future planetary missions. What we've done, flyby, orbit, land, rove across our solar system. We'd love to do that to every object. We cannot. We have to be quite selective, but what has come before informs us as to what we will do next. As we go from flyby to sample return, the cost of these missions go up. And in many regions of the solar system where we have to depend on sample return, those are the highest cost, but they are the highest science return. So in summary, this field has matured greatly in 50 years. It has actually been created by NASA because we can bring this data back to the Earth and we can bring these samples back and really see what's happening. And in fact, what we believe will happen over the next year is those important missions will be in the green areas. That will be the next big steps that the scientists will want to do. We're also seeing a lot of interdisciplinary activity. Astrophysicists want to know from planetary scientists now, as they find exoplanets, what should they be looking for? What are the atmospheres like? And why are huge planets like Jupiter in orbits that are interior to what Mercury is? There's no Jupiter like that there. But this tells us how planets evolve in a solar system, how planets migrate and move. They are not static. And that must have happened in ours. And that's also providing a new perspective on how our origin and evolution of this solar system came about. And finally, also, we're working with Earth science. As we look at Venus and as we look at Mars, it also informs us about climate change and other phenomena that are similar in those planets, those terrestrial planets. And so let me conclude with that and take perhaps a question or two. Thank you. Andy.
Jim, that was a great talk. I'm wondering, in light of the comments that were made in the last panel, where people were saying that we should expect more crises in the future that will make it very hard to plan strategically, all of that.
Sure.
From your perspective as somebody who's really on the front lines of the current crisis and fighting the good fight, and trying to implement the decadal against these budgetary obstacles, do you think we're at a point where the planetary program is in need of another reinvention? Or do we just need to be telling the story to the public more compellingly, or both, or what?
Okay, that's a good question. I'll tell you my opinion, and it may not be the right way to go. But I believe we have a fundamental foundation to move forward with, and that's the Vision and Voyages Decadal. It just started this month. We've got 10 years to step up to the plate and live that. We have also 10 years of budget cycles. Now, even though we cannot start missions that don't have a projected budget, whether the President provides it to Congress or Congress insists on it, but the President still has to provide it in his projection, we've got time to work things out. I always said success breeds success, but that actually is rather naive. It really is very naive. And it requires the community to get more involved in telling the people that pay the taxes that allow us to do these fabulous things the return on their investment. And in planetary science, it's enormous in many different ways, all the way from inspirational to perhaps a necessity, and runs the gamut. And it inspires kids. It allows them to consider more technical careers, as we've heard. You can talk to anybody in the field how they got where they are. There's some inspirational factor that does that. We all have our stories in that way, and we need to keep that going. We really need to keep that going. But the start is, in our chart, the green one, where each and every one of those elements, the fabulous stuff we do, all successful, we have a great track record. Now, several of those missions that we've built, like Juno, came on time and under cost. Grail, on time and under cost. MSL, Curiosity rover, we missed a launch window. You know, a planetary window is a blessing and a curse. It's a blessing because we got to get it done and get it off this planet. It's a curse if we miss it, it's going to cost more. And so, yeah, it overran. And we had people, even if we solved all the technical problems 1 month after the launch window expired, we'd still have to be paying for because they are needed to get the thing down to the surface. So it is a tough field to do. You know, I often, even when I talk to congressional staffers, try to give them a little feel on how tough it is. And one day I said, you know, what I don't understand is how come you can have somebody come in and build your kitchen and not stay on budget? How many kitchens have we built in this country? And of course, one of the staffers said, how'd you know I was building a kitchen and it was over budget? So this is a really tough business, but I believe now we have management techniques employed and a whole variety of tools and the oversight that we need to give us now confidence that we can tell the American public that these missions are going to stay in cost and on schedule and be more truthful than we ever have before. Wes.
Okay, Andy was the hardball pitcher. I'm going to be the softball pitcher for you, okay?
Okay.
You know, planetary exploration has been steeped since its beginning in this progressional mantra. You know,
Yeah.
flyby, then orbit, and
Right.
then land. And in the last couple of decades, we've added, rove and sample return. But given what we've learned about Mars, places like Europa and Enceladus, what do you think about adding another one, drill?
That's easy. To get the samples we want, we got to get under the surface. You know, we know the aquifers are there on Mars. Where there's water on this Earth, you can't go anywhere and find a thimbleful of water and not find life in it. That's where you got to go. We got to get under the surface. And we know that now. And it's true at Europa, too. So drill is an element of one of the tools that we need to bring with us. You bet. Yes, sir. Or wait a minute. Let me go over to Harry, and then we'll get back to you.
Harry Lambright, Maxwell School, Syracuse University. Back in the 1980s, during this drought of planetary programs, and a time when there were questions in the White House of phasing out JPL, one of the ways JPL survived was through a fairly significant work for others program. In other words, a large part of the workforce, which could not anymore be supported by NASA, was supported by the Defense Department and other agencies. In looking ahead, as you look to preserving your assets, particularly JPL, and keeping some of these geniuses that work there, are you considering the Work for Others program again?
I think the heart of to my answer to your question is balance. Every center, including our contractor facilities, need to be looking at how they can diversify and that they can balance the workload, and that's very difficult to do in tough times. And so consequently, organizations that survive are those that have work in different areas that are related, where skills can be utilized across the board in many different ways. And sometimes it increases and sometimes it decreases because of the political environment we are in. And I believe JPL is working hard to continue that process of diversification. And right now, I'm also working hard to provide funding that will enable our whole science community to be able to get back to the business of planetary science as delineated in the decadal.
Thanks.
Yeah, one more question.
You showed that beautiful picture of Itokawa. The Hayabusa mission brought samples back to Earth that
Yes, it
landed
did.
in Australia. Was there anything significant found from that mission? And I have one other question quickly. Will there ever be a conflict between NASA and planetary and asteroidal exploration and the mining group that want to go out and mine asteroids?
Okay, so let me take the sample brought back from
Hayabusa.
Hayabusa of Itokawa. We had an arrangement with the Japanese to be able to share about 10% of those samples, and those samples have come back, and many of those now are in our own archive, and we've gone through the process of having them sent out to many people in the community. Right now, one of the top things that have coming out of that is an understanding of what we would call space weathering. All right? These bodies exist in the solar system, are bathed in the solar wind for billions of years. And so the solar wind, it impacts, gets embedded in the material, and so when we take a spectrum of it, the spectrum doesn't give us what really the material is all about. Because of the space weathering, we get different spectral features than we know how to interpret. So with the samples now in hand, we now can separate space weather effects from actual mineralogy, which is what we want to get at. Now, we've seen that most recently with another rubble pile that actually passed by the Earth, and it passed close enough that the gravitation of the Earth rearranged it. And the spectrum before it encountered closest approach, and the spectrum after were night and day. And it's because the pristine material got sifted to the top, and we were able to look at it. And that's also another excellent example of how we're now looking at the environment and the space weathering and what it does to those bodies.
Thank you. Remember my other question?
Uh,
Conflict between planetary astronomers and the possible mining?
Yeah, oh yeah, the mining group. Yeah. Now that we know much more about material in space, that's a resource. Whether there are commercial companies or their material is needed to support human exploration, both those groups will need to know what's out there. We're at an infancy, really, in understanding. We got a lot to do before we can say, this is a place you need to go to mine this tungsten or whatever it happens to be that they might be looking for. I see no conflict, certainly not over the next 10 years.
Thank you.
You're very welcome. All right, I think that's the end of the question period. However, what's really critical, that from my perspective, is that I've told you from a science perspective what's going on, and in many ways, we're really down in the weeds. We're really looking at what we're doing and how we're doing it, and it's hard for us to tell the story. It's really the historians, it's really you that have a job to do also, to write about how these programs are connected, the things that we're finding out, and help relay that to the general population and the public. And that's one of the reasons why I'm really excited about this particular anniversary, bringing us together to be able to talk about these things. Now with that, let me ask Stephen Williams to provide me this set of information that I desperately want to do next. All right. The Planetary Science Division at NASA headquarters, from time to time, takes the opportunity to really recognize major achievements that have occurred in the field of planetary science. And I'm delighted to be able to do that today with many people that are sitting in this audience that have really made a difference. And in fact, the inscription says, in recognition and appreciation of your leadership towards solar system exploration and discovery, you have made a difference. And the first awardee is Joe Alexander. I saw him here. He's here. Where is he at? Joe. Well, as a scientist, you've been working hard over the years, and you've made a lot of things happen, heading the group at Goddard and doing so well that it's very much appreciated. Amazing. And indeed, you have made a difference. Thank you for everything you've done. The next individual I'd like to honor, and it's also my great pleasure knowing this individual actually for only a part of his career, is Jim Burke. Jim? Oh, he was here. All right, all right. Well, you'll learn much more about Jim as he's one of the panelists, I believe, tomorrow afternoon. But indeed, Jim not only has been involved in planetary missions early on, his dedication to educating the next generation is absolutely unbelievable and needs to be recognized for all he's done for that. So, Jim, I know your ears are burning. The next individual is Stephen Dick. And as I mentioned earlier, the history of the solar system and how we learn and understand what we're doing is very important. You've made a major difference with many of the writings that you have done. Thank you very much. Okay, my pleasure. You know, some of the fantastic things that we do in planetary science is start out with a particular mission and figure out under tough budget constraints what else we can do with it. And the master of being able to do that is the next awardee, and that's Bob Farquhar. Bob's here. There he is. My first interaction with Bob was when he was involved in moving the IC-3 mission from up front in the solar wind to fly by Comet Giacobini's inner. Okay, we'll do it this way. Bob has to do it his own way, and that hasn't changed. And Bob is...
I like to be known as NASA's #1 troublemaker.
Yes, he is. But in a good way. Thank you so much. My pleasure. Yeah, watch out for the step. The next one I'd like to recognize is Scott Hubbard. Shocked him. Yes, right. Scott is an individual of many talents. And one of those talents that he's going to talk about is indeed the ability to help put back a program, sell that program, make it happen. And it's just reaped enormous benefits for us and the community and this nation. So, Scott, thanks a million.
Well, thank you.
My pleasure.
Jim?
Jim Burke. Great. Jim, I just gave you an award. Here we go. Watch out for this guy.
That wonderful movie where the guy was in the crapper when they were trying to do something. All right.
Okay. Jim, thanks so much for all your work in NASA and also educating that next generation.
Yeah. Wonderful. Oh, boy. What a treat. Look at that.
Thanks, Jim.
Wow.
Great. Okay, now watch this.
I'm a lucky fellow, yeah.
The next individual is also someone I've known for many, many years, who's near and dear to my heart, has made a major contribution to the field in many ways, and that's Wes Huntress. Just got a few more here. One scientist that I believe has really epitomized the best in many different ways in terms of being a solid scientist, working hard to relate that science, and talking about it in a way that many can understand it, not directly in their field, and that's Torrance Johnson. There he is. the next individual is really quite unique. His ability to, his driving ability to be part of a science community and exemplify the best as a scientist, as a program manager, and as an educator, and do it in Russia. And that's Mikhail Morov. Mikhail?
Thank you.
One of the things that is difficult to explain to people, apparently, is how expensive our space systems are. And in this particular way, you know, we have to take our power with us. We have to go to the far reaches of the solar system and take plutonium. And that's not cheap. And the systems that we have to develop that manage that type of resource is also very expensive. And it's a delight to give Ralph McNutt the next award for how he has worked hard to tell the story of radioisotope power systems in addition to being an outstanding scientist. Ralph, I thank you. The last recipient really needs no introduction. This individual has been what I would call founding father of planetary science and has managed a major center, JPL, has managed 2 major spacecraft and many others in a way that has really stirred interest and excitement. And my first foray into planetary science was writing papers about Jupiter's decametric and kilometric radiation from the Voyagers. This individual is Ed Stone. Okay, we have a request for a real quick group picture. Do we have time for that? We're over? All right, okay. If we could bring everybody up for a real quick group picture, that would be super, and then we'll get off the stage. Yeah, everyone that got an award. Sorry, I wasn't clear about that.